Last class we have introduced the matrix mechanics for harmonic oscillator and come to the conclusion that the Hamiltonian can be written in terms of the raising and lowering operator, and as this, where a plus minus is defined by this, and that the energy levels are equispaced and this is the energy value. So in fact we can write that H operating on En is equal to En, where En is equal to N plus half H cross omega En. Now we write Hamiltonian as H cross omega A plus A minus plus half. This is the Hamiltonian operating on En gives you N plus half H cross omega En. Now this term cancels on either sides, or we arrived at A plus A minus operating on En is equal to N En. The H cross omega cancels out, or the number operator N operating on the energy eigenket gives you En, from which we go to the number representation as N operator operating on the eigenket N is equal to, this N is the number of photons. In this term, the H can be written as that is, we say that the system, when it is in the eigenstate n, or in a quantum number state n, it has exactly n photons, each of energy h nu. So the total photon energy is this, which when added up with the 0 point energy gives the total energy of the system. So the very handy notation for this these two operator comes out to be this: N operator operating on N is equal to N times and the Hamiltonian operating in num. This earlier we have written it energy basis, now we have written it in the number representation. That is to say, the energy eigenket may be written as these, or as well as in terms of this. This is energy eigen in terms in energy basis, and this is in number basis, equivalent representation. Now we shall continue with the number representation, which is much easier to write, because you have to write E then suffix N, and then we need to write only N. So we consider the A operator operating on state N. It means that the one photon will be added to the system, so we write it is C plus some constant times N plus 1. The complex conjugate relation or Hermitian conjugate relation of this is N A plus dagger, which is A minus, is equal to this is N plus 1 C plus star. Now if we take the Hermitian conjugate means transposition followed by the complex conjugation. So transposition, this column matrix becomes a row matrix, which is the row matrix, and you take the this is the square matrix, so we will take the Hermitian conjugate of it. The Hermitian conjugate of A plus is A minus, and here we will have this column matrix will become a row matrix, and C is a constant which may be complex. So this is the result. If we take the product of these two, we get on the left hand side in A minus A plus n is equal to since C is a constant, not operator, so we can take it out. So this is C plus modulus square n plus. So this is the vector, the magnitude of the vector. If we assume it to be normalized, then this is C plus modulus square. In other words, C plus modulus square is n A minus A plus n. But we know our relation in terms of the number operator. A number operator, this number operator, remember that it is A plus A minus. So we use the commutator relation of A plus A minus. A plus A minus is equal to minus 1. That is A plus A minus if we take it on the other side, we will have A minus A plus is equal to A plus A minus plus 1. So this relation becomes now this is the number operator. Keep this fixed. When this operates on n, we will have first let me break it into two terms. That will be easier for you. And then this is n. And this part, when this operates on, this is number operator operating on n. This is 1, and this is so we see that this is we summarize that A plus operating on state n gives you n plus 1, and the kit is increased by 1. Similarly, if we consider that A minus operating on a state n gives you C minus, and the photon number is increased by 1. If we take the Hermitian conjugate of it, it is A plus, because the Hermitian conjugate of A minus is A plus. If we take the inner product of this of these two relations, we get n A plus A minus n is equal to this is simply C minus star n minus 1 n minus 1. When they are orthogonal, this is simply C minus modulus square, or C minus modulus square is n A plus A minus n, which is already in the number is in terms of the number representation. So this is So we see that n minus root 2, root n. Oh, sorry. A minus operating on n gives you, these are the two relations. At this point I want to find out few known relations that we have done earlier. First thing is that a plus is equal to 1 by root 2 q minus ip, and a minus is equal to 1 upon root 2 q plus ip. So if we add these two, a plus a minus, the pp goes. Similarly, we find that p operator is 1 upon root 2 this two. So we want to find out the q operator when operates on an eigenstate n. Exactly, we do not know how this operation is, but we can replace q operator in terms of raising and lowering operators. So this becomes so this is 1 upon root 2 a minus operating on n is this, a plus operating on this. This recurrence relation we have arrived at from the property of Hermitian Hermite polynomial. Here we have not yet spelt about Hermite polynomial. Still we have arrived at the same result. Now come to the p operator. P operator operating on n is this relation we arrive from the property of the Hermitian Hermite polynomial, that is hn of x is equal to 2n hn minus 1 of x. From this relation here it has been obtained from entirely other consideration, and this is my del x basically, del q basically. Now I come to the conclusion that ground state. I am interested now. I am looking for the ground states. Ground state is denoted in this notation in number representation is 0, and it is represented by h operating on a number state is half h cross omega 0. Now if we write the Hamiltonian in the form a plus a minus plus half h cross omega operating on 0 gives you so here from we find that The definition of ground state is A minus operating on this is a null ket, as we have obtained earlier. And now now we write this equation explicitly, the form of, so we write the ground state is that for which this is 0, and for A minus we write this is the signature of ground state. Before proceeding further, we must consider let me write this ground state property. Now we want to write the ground state then either in position basis, in x basis. We have Q operator is equal to Q itself, P operator is equal to minus I ddq, and the wave function, 0 wave function, is equivalent to psi 0 of Q. These are the relations. So we plug all these things into it. At this minus 1 upon root 2 is not a deciding factor here, so we ignore it. So this is Q times, this is I square minus I square, so this is plus 1. If we solve it, this is a very trivial solution. If we solve it, we get Q square by 2. The actual normalization, when we do it, the normalization, that is Q0 star Q0 dq from minus infinity to plus infinity is equal to 1. This gives you So this is the general definition of ground state in any basis. When we project it into the position basis, the result is this. Now we shall see in momentum basis, in P basis. We have P operator is equivalent to P, and Q operator is equal to plus I ddp, and the wave function is psi 0 tilde of P. So the equation becomes, this equation becomes I taken common, P plus ddp operating on psi 0 tilde of P is equal to 0. When we solve this differential equation and normalize it, we get psi 0 P is equal to pi to the power minus 1/4 e to the power minus p square by 2. This result we have obtained earlier using the Schrodinger picture. Now coming to the excited test. So we have reproduced the ground state in position basis as well as its momentum basis. Note that we need not to solve two different formalism at the same time. The same formalism up to this, the same equation, then the special case has been used. So ground state problem is over. Now we shall go to excited states problem. And you remember that the ground state is psi 0 of q is equal to pi to the power minus 1/4 e to the power minus q square by 2, and psi 0 tilde of p is equal to pi to the power minus 1/4 e to the power p square by 2. Now excited states coming to here we have the information about the ground state, that is 1/√2 q plus I p when operates on the g. This is equal to 0. For excited states, linear harmonic oscillator, we use this relation. So we write that n plus 1 eigenket can be written as root over n plus 1 a plus operating on n. So first excited state, excited state is 1 is equal to 1/1 a plus operating on the ground state. Now come to the second excited state, say 2. For this we put this equation n is equal to 2, so this is 1/square root of 2 a plus operating on 1. When 1 we replace 1 in terms of ground state, we get it 1/square root of 2 a plus operating twice on the ground state. And 3, if we calculate 3, the trend will be clear. In 3 we have to put n is equal to 2, so this is 1/√3 a plus operating on 2, and when we replace 2 in terms of this factor, the denominator factor becomes very clear. This is 3 factorial a plus operating thrice on the ground state. So in general we can go on like this, and to get a n is equal to 1/n factorial a plus operating n times on the ground state. This is the definition of excited states. So we summarize excited states as now recall the definition of a plus. A plus is defined as 1/√2 q minus ip. So this can be written as this is the definition of excited states, as simple as this. Now we go to the position basis and see what happens. Q operator is Q and P operator is minus I ddq, and psi 0 is, this is the definition. So we write, and and this is equivalent to sine of q. So left hand side, sine of q is equal to this part 1 upon 2 to the power n factorial n under square root, and then this factor q minus, this is plus and minus square, so this is minus ddq operating in terms on e to the power, ground state wave function is pi to the power minus 4 e to the power q square by 2. This is for the ground state wave function. So if we phi to the power 4, the factor is exactly as we have obtained there. Now there is an interesting property of Harmonic polynomial. We have e to the power plus x square by 2 x ddx operating in terms on e to the power x square by 2 is simply hn of x. So we find that the state is the famous Harmonic wave function. We have this term, and when this is taken on the other side, this becomes, so this can be written as this x ddx operating in terms on e to the power minus x square by 2 is hn of x e to the power minus x square by 2. So this is the result. Now coming to the momentum basis. So we write that this we get psi n of q is equal to root pi 2 to the power n factorial to the power half hn q e to the power minus q square by 2. So the same, exactly the same wave function and same energy, everything has been recasted in momentum basis. P operator is equal to P itself. Q operator is equal to plus I ddp. Then the ground state is psi tilde of P, which is pi to the power minus 1 by 4 e to the power p square by 2, and the state n is actually psi n tilde of p. Now coming to this definition, psi n tilde of p is equal to, consider this factor, and this comes from the minus up. Then the operator, this is I ddp minus I to the power n will this is the constant term. Then if we interchange, this is this will become p minus ddp and the result will be minus I to the power n. This goes within the normalization factor. This leads to the hn of p e to the power minus p square by 2 by the techniques that we have shown earlier. This is a phase factor. This phase factor we cannot determine, because whenever we normalize a function, we find that when we go to normalization, it will be minus I to the power 2n, and which is equal to 1. So the only a phase factor is there. This is not, we cannot determine in quantum mechanics. So we have reproduced the entire wave functions of ground state and excited states in position basis as well as in momentum basis. There is one more thing left in this, is the matrix element, that I will consider in the next class.